Hello again. Last session we started thinking about what information we can glean from a data set, and we took a look at these parameters: average, variability, in this case standard deviation, median and mode. These parameters are very useful when we're looking at a single standalone data set, when we just want to know what is happening in this instance. However, a common scenario is that we need information to help us make a decision about the difference between two situations, or treatments as they are sometimes called by statisticians. How can we tell whether something has changed, or whether doing something differently from our current system will cause a positive or negative change? For example, we may want to know if a new grazing regime, for example strip grazing, affects the quality and/or quantity of milk from our cows, or if a new watering regime will affect our total yield of potatoes, or how a new, less intensive cultivation method influences our apple crop in terms of average size distribution and variability, and how this translates to processing efficiency and sales. And so to find this out, we need to think about the data we need to collect, and we need to start collecting it. In earlier sessions, we've talked about the compromises that need to be made when collecting a set of data from a given population. For example, all the apples in a crop, all the potatoes in a paddock, all the customers who buy your yogurt. We've talked about having to work with a sample, a data set that is smaller, and often much, much smaller than the original population. We've talked about the importance of accuracy and precision in determining the worth of our data set. And we've talked about how the variability of values within a given data set, be it related to the precision of our measurements or the natural variation in that population, will affect what we can interpret. With all these parameters to consider, how can we know how much data, how many data points we need to collect to be confident that we will detect a real difference between our current way of doing things and the proposed new way? This is often the crux of the design and application of data collection exercises. Now, this will get a little technical, but it is an important part of making sure that the data we collect actually is able to help us answer our questions. So basically, we need to understand the nature of the compromise between the cost of collecting data, be it in people's time, lost productivity, destroyed samples, you name it, gathering data is expensive, and our confidence in that data. To help us in this, we can do what's called a power analysis, which in most situations is where we, or more correctly a software package, calculate the necessary sample size based on our knowledge of the expected or relevant effect size, a parameter called alpha, which is the probability that we will find a significant effect where there isn't one. We want this to be low, and it's usually set at 5%. And a parameter called power, which is the probability that we will find a significant effect when there is one, and we want this to be high, and it's usually set at 80%. Now, because alpha and power parameters are usually set at 5% and 80% respectively, the important aspect to consider is what we call effect size. To calculate the effect size in our data, we need to have an idea or be able to estimate the averages and standard deviations of the two data sets you are comparing. To do this, you might have some pilot data, or have access to data from similar experiments that others have done, or you might just have to guess, but I wouldn't recommend this. The effect size is calculated by dividing the difference in the average values of each data set by the pooled standard deviation, which is often also called sigma, and is calculated by the formula on the screen now. What this formula says is that to calculate the pooled standard deviation, we need to square the standard deviations of each data set, add these together, divide this by 2, and then take the square root of all of this. It's a tad complicated, but important. It's worth calculating the effect size in its own right, as this will give you an idea of the analytical worth of your data. For instance, an effect size of 0.2 is considered small, which means significant differences in your data will be hard to detect. An effect size of 0.5 is considered to be medium, while an effect size of 0.8 is considered large. And you'll see from this formula that the more variability there is in your data sets, the larger will be the pooled standard deviation, and the smaller, and therefore less useful, will be your effect size. Now, I reckon you've got the drift of this now, and I know you'll learn more by doing more than listening. So I suggest you head over to an online power analysis calculator like this one and have a play. And just a note here, use the one-sided test option. because you are just looking for a pass-fail answer. Spend some time looking at how the recommended sample sizes vary with changes to the averages of the two data sets and to changes in the pooled standard deviation.